or the end of the day, or at some point, so I don't have to put a 0 in. Odd that those dots aren't filled in either. Anyway, so this is, yours also says D4, doesn't it? That's probably, you know, I made some changes and I never say this. Yeah, that is correct. This is D1 if it's BC, but it's D4 if it's AB. So it's the same packet, just depends on where it falls for the different classes. So we got D4. We have our last VT, the extreme value theorem. A lot of differences between this one and the other two. The other two kind of fit in the same category. We'll talk a little bit about that as we go along. And really the EVT fits along with this question where we talk about absolute extrema. So the absolute maximum of a function, the absolute minimum of a function. So a couple things. When we're talking about relative maxes and relative minimums, we're talking about, at the very least, a very small window of x. So the definition of a relative minimum is at that x value, I'm actually recording and there's nobody to watch this, so that's good too. At that x value, that is the largest that function gets in a very small area around it. That's the definition of a relative maximum. Now, could it be even better? Yeah, because look at that thing. Does the function ever get any bigger than that? No. So that is a relative maximum. Based on the definition of a relative maximum, where we're thinking just a small window around that x value, the function is never going to be bigger. So obviously, you know, there's lots of cases where a relative maximum is actually also the absolute maximum. But the minimum requirement for a relative is just a small window around it. But when we're thinking about absolute minimums and maximums, we're thinking of big picture. So we generally give you a domain. We want to say between this x value and this x value, when is the function the biggest? When is the function the smallest? That's when we're talking about absolute extrema. We can lose the word absolute. So if it says what's the maximum value of the function, that's the same as saying what's the absolute maximum of the function. I can't lose the word relative. I have to use the word relative if I'm asking for a relative min or max. So the other thing here, and again, I don't know why all of my dots are open on this graph. It didn't hit me until I just looked at it now that it looks weird. But you can see we have an example also on this graph of a relative minimum that is only a relative minimum. The function actually goes lower at the starting point, right? That is the lowest value it hits. It starts out the lowest that it'll ever be. It increases, decreases, increases again, but it never gets as low as that starting value. So something coming up later, we'll talk about that. Absolute minimums and maximums can happen at endpoints, or they could be where there are other relative minimums and maximums. All right. So basically the EVT, the extreme value theorem, tells us whether or not we will have absolute minimums and maximums. Because depending on how the function is defined, depending on the interval we look at, there doesn't necessarily need to be an absolute minimum or an absolute maximum. And just like any of the other theorems, there are conditions and there's a conclusion. The big one is that you're defined on a closed interval from A to B. In order to guarantee an absolute min or an absolute max, we have to lock ourselves into a closed interval. So we've got two solid endpoints on either side, and we need to be continuous on that closed interval. A good book definition probably wouldn't separate these two conditions, but they would write it all as one sentence. They would say the function is continuous on a closed interval from A to B, but we really need to think about in that sentence those two separate things. 9 times out of 10, if we're going to use an EVT, they're giving us this interval because, you know, it's not something that we would come up with on our own. So they are specifically saying it's this closed interval from A to B. And then it's our job to say, I'm doing EVT. Am I continuous? If that is the case, your function will have an absolute minimum and an absolute maximum guaranteed. Okay. Otherwise, just like the MVT and the IVT, maybe. Right? We never make the reverse conclusion from any of our VTs when say, no, that didn't happen, because it still could happen. It's just not guaranteed. So let's take a look at a couple examples of some functions that are defined in a couple different ways. What is going on with my dots on? I feel like something in the process took my solidness out of my dots. Oh yeah, because your dots are solid on your, okay. So that's what's going on. It's just something that happened in Word or Acrobat. So you've got a bunch more dots filled in on your picture than for whatever reason happened on my screen. It's every dot here but the bottom one, right? Cool. And that does match the function definition on the bottom. Those two dots are open in number 2. Yep. There are no dots on number 3 because it's from negative infinity to infinity. And then on number 4, those two dots are filled in. That's really weird. I haven't had that happen before.
Why is this one open? This one's not.
Oh, and now they're different. And this should be, defined on the closed. And that is a legit typo. So that last one's on me. Those should be closed parentheses on the last example. Like I said, yeah, most of the stuff has gone through a couple times of me teaching it, so a lot of these things have been caught. This is a new one. So, okay. So we're going to answer 2 questions on both of these. Are the EVD conditions met or not met? And do we have relative minimums and maximums? So let's start with the first one. Does that hit have a relative max? Or sorry, I said relative, I should be saying absolute. This is really about absolutes. Does the function in number 1 have an absolute maximum value? Yes. What is that value? 2. So f of x has an absolute max. Let's get, I hate writing in black. All right. Has an absolute max of 2 at x equals 0. That's kind of going to be what we practice writing for these problems. Sometimes they ask for the value. Sometimes they ask for when or where it happens, what the x value is. So if you write both of them, you've covered all of your bases. So we have an absolute max of 2 at x equals 0. Does this function have an absolute minimum? No. So what if it has an absolute minimum? You can say a number that this function hits, and you cannot say any numbers lower than it. This is a little bit of a thinker. Can you give me a number that's the lowest value that function achieves? So Franklin said 0.00001. Right. So but that's the key. You can't actually say a number that's the smallest, because Franklin can say 5 zeros and a 1, and I could say, well, what about 0.6 zeros and a 1? But that's still not the minimum, because then I could say, what about 0.7 zeros and a 1? So this never achieves an absolute minimum value. If it was filled in, I mean, it wouldn't be a function anymore. I'd have to open up the top. If that point was filled in, it would hit an absolute minimum of 0. But this function does not have 0. You could never plug an x value in and actually get 0 out of it. But you could get 0.50,000 zeros and a 1, which is a really, really tiny number. But so yeah, so there is no absolute minimum on this function. So obviously this breaks an EVT condition. Which of our 2 conditions does it break? It's not continuous. No EVT because it's not continuous. Yep. And again, just like MVT and IVT, it hit an absolute max. There's nothing about these VTs that says it can't happen, because it's just, they're all just guaranteeing functions. Okay. Second one, x squared on -1 to 1. My open dots look weird on the screen. Like they look right on your paper. Yeah, whatever. Anyway, what does that hit? Yeah. Yeah, that does have an absolute minimum of 0. This function, I mean, and this is why I give the function definition as well. The f of 0 is 0, and you are not going to get any lower value than 0 out of x squared. So this does have an absolute min of 0 at x equals 0. Does it have an absolute max? No. Again, you can get to 0.50,009 if you want to, but then I could put 0.50,001 nines, and that is a bigger number. So no absolute max. And which IVT condition is broken? Yeah, we broke the closed interval. It's defined on an open interval. Alrighty. I really think this next idea, this next one, kind of gets at the reason to why we use open parentheses for negative infinity and positive infinity. So there's the graph of sine of pi x plus 1 on the interval from negative infinity to infinity. So we do not have closed endpoints, and we are, I cut the graph off, but we're considering this graph going forever in every direction. Does it have an absolute max? Does it have an absolute maximum? You can only have one absolute maximum.
Oh, no. Yes?
Yes, the absolute maximum is 2, right?
Oh,
It occurs at multiple places. So details, just, this is brand new to you guys today, but I'm saying those just to kind of bring out the details. It has an absolute maximum of 2, and that happens a whole lot of times, but it has one absolute maximum, and that absolute maximum is 2. So if I'm asking you for the absolute maximum, I'm asking you for the function value, and I have to use more words to say when it happens. So we have an absolute maximum of 2. So sine of pi x, what x value is getting us there? Yeah, 1/2, right? Yeah, this is going to be 1/2. This is going to be negative 1/2, but this function goes on forever. So the next one would happen at, but that would be the minimum, wouldn't it? 2.5, yeah. So they're happening at 1/2, 5/2, 7/2. Because it's skipping. You're hitting critical values at 1/2, 3/2, 5/2, but then you have to skip every other critical value
You
too.
use a word that means like when it gets back to the same point, right?
Say it again.
Like the period of a function is when it gets to the
Correct.
same point.
Yep. Period. Yeah, we're talking about the period of the function. So that happens at x equals plus or minus 1/2, 5/2, 7/2. ... There's probably better notation to write that. But
why is it plus or minus? Shouldn't it only be...
Oh, shoot, because it's different. It is different on the other side. Oh, so I actually have to do it this way. Good catch. I didn't think that through. At x equals, so we're gonna have to label the negative. So it happened at -3, which means it would also happen at -7? Negative, because it's skipping over 1. So -7/2. And I think maybe me having 7/2 on the other side was wrong then. Yeah. All right, so let's get this right. -7/2, -3/2, 1/2, 5/2. So I skipped 1. That should be good enough. ... And let's get a ... at the beginning as well.
Would they reduce something like this to be an open interval?
I don't think, no, I think this is more, I don't think this would be the way the question would be asked. So if it would, I would show you a better notation to write what I have there. I mean, that is solid enough notation. And then obviously we hit an absolute min. The minimum is only one number, it's 0. It just happens to happen at a whole bunch of times. Yeah, it is. It's just the opposites of those. So I'm gonna actually take my list and run it backwards and say -5/2. All the things we skipped. We skipped -5/2. We skipped -1/2. And then we skipped, next one should be +3/2. And then +7/2. Then my ... at the beginning as well. So, okay. And were either of those things guaranteed by the EVT? No, because our interval's open, right? So think about this. Think about sine x as an example where we, despite the EVT, we hit both a minimum and a maximum. But just think of something like x cubed. Does x cubed have a maximum?
No.
Oh, he said, yeah. No, it goes up forever, right? Yeah, put 100 in, you'll get 100 with 6 zeros after it. Put 1,000 in, you'll get 1 with 6 zeros. Put 1,000, you'll get 1 with 3 times 3 is 9 zeros after it. You can get as big as you want. And I picked x cubed because it also doesn't have a minimum, because the negatives legit give you negatives, and for the exact same reason. So, if we were able to, if we in our notation closed parentheses on the infinities, then that would be an example of the IVT not, or the EVT not working. So that's just another insight onto why we use open parentheses with infinities, because it would kind of break what we're saying here with the EVT. Okay, and then last but not least, we haven't had one hit the EVT yet. Does x squared on the interval from -1 to 1 meet the IVT conditions?
Yeah.
The EVT conditions. I'm just going to keep saying IVT no matter what, but I generally mean the EVT. Yes, it does meet our conditions. It is continuous. It is on a closed interval. So for note-taking purposes, I'm just going to write EVT check mark at the bottom. That is not an answer I would ever put on an FRQ. What's that?
We're going to get any sentence for that?
I think so. I think I've kind of given you it as the absolute mins and the absolute maxes. That's our sentence, yeah. So anyway, our absolute min is 0 of 0 at x equals 0, and our max is 1 at x equals plus or minus 1. So that hit both. It was guaranteed to hit both because it was a continuous function defined on a closed interval. Okay. So those are just some of the ideas. That's why we need those two conditions. I've kind of hit almost everything in there. You'll see one more way to break the conditions in the exercises. Okay, so when it comes to the three questions, IVT and MVT are very similar. We list out the conditions and we say that it guarantees that there is a value, and we don't always need to find that value. As a matter of fact, with IVT, it's very rare that we need to find that value. MVT questions can kind of go both ways. You guys had a question on your last test where it said, where does the instantaneous rate of change equal the average rate of change? That was the MVT question. Rather than asking you to list the conditions and say that it was guaranteed to happen, those conditions were met. If you thought about them, you probably didn't. Why would you? Those conditions were met. So there was a spot, and it was your job to use Desmos to find when the derivative equaled the average rate of change, the secant line. So MVT kind of goes both ways. Honestly, with EVT, it's usually just find the value. So there aren't very many times where it's like, oh, list the condition, make the conclusion with EVT. It's literally just find the x value where the absolute maximum is, find the x value where the absolute minimum is. So what we do, we actually have kind of a separate thing. This is the main thing. Like when you get to this question, I will probably not, when we're reviewing end of the year, I probably won't say, oh, this is a candidates test question. I'll say it's an EVT question. Basically, there's only two different types of spots where you can hit a max or a min. Either where you have a relative max or a min, or maybe it's just one of the endpoints. So what these questions involve us doing is we have to figure out what those things are. What are the endpoints? They're given to us. And then what are the critical values? We have to figure those out. And then we just go through those numbers and pick the biggest one or the smallest one if we have to pick a minimum. And that's what the candidates test is. So if you have a function that's continuous on a closed interval from A to B, which will be given to you, you're going to identify the critical values, make a table using the endpoints given and the critical values, go back to your original function, that's important, know your function, and plug it in and see what happens. And then just, look at the table. What's the biggest? What's the smallest? The last part's kind of like the dumb part of it. Like, oh, there it is. Found it. That's the biggest value. There it is. That's the smallest value. This is going to be important today, and this is going to be important in Unit E, which is where we're going to next. In Unit E, most of the times, we're not going to be given the original function. We're going to be given f prime, but we'll be working in reverse, right? Our job in units A to D, I give you the function, you find the derivative. Once we hit unit E, I give you the derivative, and we reverse the process. We will integrate to find the original function, right? That's kind of the way this class is laid out. So this pops back up big time in the next unit, and it pops up big time in that way in the FRQs. So a lot of times when we're doing this candidates test, this part 3 is actually bigger than it's going to be today because we're going to have to integrate to find the original function and plug it into that. So, our conclusion, this is the sentence that Franklin kind of was alluding to before. Once we do that, we'll say the absolute minimum is the function value and where it occurred. And we will say either maximum or minimum depending on what we're being asked. Okay, so let's do a couple examples. Find the absolute extrema for the following functions. This is literally, well, anytime it's x squared, this is something you guys have done before in functions, or even algebra 2. In algebra 2, you identified the vertex of a parabola. We're just going to do it with calculus. We don't have to remember any kind of fancy formula. Wherever that derivative is 0, that's going to be where the vertex is. So it's a little bit of a, less to remember, I think, when we get to calculus. So anyway, we've got a parabola. It's defined on a closed interval, so we're only looking at a piece of this parabola. We need to first identify the critical values. So we need to find f prime of x. Jump in here. I write better when it's bigger. And that f prime is 4x minus 8. And we want to know when that equals 0 because those are critical values. That happens when x equals, last time I checked, which means that the only candidates for absolute min and absolute max are the endpoints 0 and 3 and the critical value that we just found, which is 2. And since this is a parabola, that's just going to be the vertex. So we've got 0, 2, and 3. We've got x. We've got f of x. And now let's plug those into f of x. Plug back into the original function because that's what we were talking about. What's the biggest value this thing could hit? What's the smallest value this thing can hit? Easy one. Plug 0 in, you get 1. Less easy one. Plug 2 in. Negative 7 sounds good because we ended up with 8 minus 16 plus 1. And that's negative 7. And we get negative 5 for 3 because we do 9, 18 minus 24 and then plus 1, negative 5. Good? Okay. Yep. Oh, it does. Yeah. I heard. Yeah, that's what I heard. I just didn't know what we were thinking. Got it. Yep. So there's our table. There's nowhere else that you could have had a relative min or an absolute min or an absolute max. So that tells us that the lowest value this function can hit is lowest, negative 7, and the highest is 1. Yeah. Sure.
Just do the same thing with the sign chart.
So that's a good question, but how would you know that it hit its lowest value, its highest value at 0 versus 3? So yeah, so one of these you can find with the sign chart, but the other one you can't. And actually, when we get to example 4, I've been planning on bringing that out. So let's see, we have an absolute max at x equals 0. Max with max of at x equals 0 of 1 at x equals 0. And an absolute min of negative 7. At x equals 2. Cool. Yeah, no. So yeah, there are definitely some shortcuts you can take, especially when you're working with polynomials. And like I said, we'll highlight that in number 4. And back in B11, everybody's favorite, that was the Desmos activity with the real world problems. We had absolute minimum and maximum questions, and that is how we solved them. If you do have something that only goes from, in this case, decreasing to increasing, then you can find the absolute minimum without having to do this. Now, the max would be a different story. Okay, but it would kind of have to be an endpoint. Here's a good one. Do I have to use the quotient rule to solve this? No, because I have, it's really, in a way, just 1/2 x squared minus 1 squared. Could I expand that out and treat it like a polynomial? If I wanted to, yeah, it wouldn't be awful. It's just foiling. I'm not going to do it that way. I'm going to find my derivative the normal way. What rule do I have to use? Chain rule. Yep. I have an argument, x squared minus 1, and I have a function that is square that thing. So we end up with 1/2 the derivative of the argument, which is 2x. And then I need to do the power rule, which means I've got hold on a second, I missed my half there, sorry. 1/2 that was there, that's just a coefficient, times 2x, that's a highlighter, not a pen. I'm doing really good here. There we go. And then the power rule tells me I need another 2, yep. X squared minus 1 to the 1 power, yeah, so just x squared minus 1. So 2 of those 2's can cancel, and I end up with 2x, x squared minus 1, right? Advantage to doing the chain rule is I'm factored already. I mean, not fully factored, but I am factored. So we end up with 2x, x plus 1, x minus 1. Yep.
Oh, yeah, I didn't think about that.
Yep. Because we need to find the critical values, right?
Yeah.
You can identify that they are plus or minus 1. If not, do the factoring too. You need the factoring if you're doing a sign chart for sure. That's kind of what threw us on, was it the test? That's something. We definitely got thrown by that on something, making the sign chart. Oh, it was the last quiz. It was the Unit C quiz where it was 4x squared minus 1. Everybody was able to find the value, but then the sign charts were all wrong. But since we don't need a sign chart, if you can identify plus or minus 1, we are good here. So we need a table with, I believe, 5 values, because we have x equals 0, x equals plus or minus 1 is our critical values, and all of those are in the interval, right? If any of these came out and they weren't in the interval, we could throw them away. If I had an x equals 7 down there, 7 is between -3 and 2, so we wouldn't care about it. So we have x, we have g of x, we need -3, -1, 0, +1, and 2. 3 critical values, 2 endpoints, 5 golden rings. Yep. I'll do the easy one for you. I'll plug 0 in. 0 minus 1 squared is 1. And divided by 2 is 1/2. Do the other 2 easy ones for you. -1 and 1 are both going to give you 0, right?
Yeah.
Yeah.
Check, you get them 32. Have you drawn the first one? Yeah.
Yep. 32 even?
Yeah.
Oh, yeah. 9 minus 1 is 8. 8 squared, 64, yeah. Yep. Okay, gives you 32. And 2 gives you 9/2. Yep. Oh, cool. So our minimum value is, and our max value is 32. Yep. Is there anything stopping me, especially me, to checking this in Desmos? Nope. So let's do that. Alrighty, get that nonsense out of there. Go back to home. And our function was 1/2 the quantity
We found a problem.
Say what you find.
Example 3C. H of x equals
H of x equals h of x.
Oh my god.
Oh.
Did I double it?
Yeah.
Yeah, it does. It's nothing wrong with that. There is absolutely nothing wrong with that. Hey, guess what? It's still recording. That's pretty awesome. Just have to get this back up.
We can heard your mic all the time.
All right. So we need to restrict this from -3 to 2, right?
Yes.
-3 less than or equal to x less than or equal to 2.
What is that? How you do it?
Yeah, bracket notation. Yep.
I don't actually.
All right. Oh, I do have. Yeah. I definitely need to. One of my things today is to talk to somebody who matters about touchscreen Chromebooks because you guys need to be able to do that at some point.
Oh, especially for calculus, being able to stretch out
Right.
the
Like they don't need to buy 100 of them; they need to buy 20. Do they? I'll use that run too.
I actually despise the esports team because
Oh, they're esports.
AP
team.
computer science last year without
Yeah.
like good computers. Without what? Like good computers.
All right.